I want to say good morning and welcome everybody to Engineering Tomorrow's Space Day. Today you are so fortunate because we have amazing NASA presenters, Betsy Portman and Milton Davis, who are going to be leading today, and they're going to be with us the entire day. So if you have any questions during the build, you'll be able to ask them any questions you have. I'm going to just reiterate to remember to please engage with us in chat. We want to hear from you all if you have any questions or comments. I know our presenters want you to engage with them as well, but I'm going to stop speaking because I am not the star of the show. Today is the Milton Davis Space Day. We're going to call it that for right now and pass it off to Mr. Milton Davis to lead us in Space Day.
Oh man, thank you so much, Monica. I am so excited to have a session with you all today. Give me a thumbs up. Can you see my screen? You see my screen? Can you give me a thumbs up? Excellent. I'm so excited. Hey, none of these presentations we do in Engineering Tomorrow are completed by an individual. It's always a team. I'm going to shout out my buddy Travis and some absolutely outstanding engineers. Lauren, who's at Penn State, now she's graduated, and Katie from the University of Notre Dame. They killed it when they helped develop this lab. But what are we doing today? You're going to have the chance to travel through spaceflight history, to learn a lot about the moon, the stars, the sun. You'll get a chance to build your own rocket launch vehicle, and you're going to navigate through a SpaceX capsule as well. We have so much in store for you, and I can't wait to see what you're going to build. But first, what type of engineering does this lab use? There's always this question about aerospace. You really can break down aerospace into two things. You have like your aeronautical engineering, which is like your planes and hypersonic flight. You hear a lot about that. Or you have your astronautical engineering, which is everything that you can imagine and do in space. But I've talked a lot about this presentation and about what you're going to do, and I didn't introduce myself. So I am Milton Davis, and this is how I became interested in STEM. It started off with RC cars. Car enthusiast. Sorry about that, Bronx International. And I didn't have access to like Instagram or Snapchat or TikTok. So I really was into basketball, definitely into football, but I also was into these RC cars and TOEs. TOEs are not feet. That's my terrible joke for the day. Hi, Steph from Decatur High School. I'm talking about theories of everything. Like, how did this entire universe come into existence? Trust me, I definitely had some struggles though. When I was in high school, one, it was a pretty rough neighborhood, and two, I just wasn't exposed to technology. I didn't hear a lot about college opportunities. So, I really was blessed that mixing those two opportunities of RC cars, which is like engineering, and theories of everything, which is all things space, we really landed on aerospace engineering. And I was blessed to obtain an internship at NASA Goddard Space Flight Center. I've been there since 2001. Yes, that means I'm pretty old. 2001, and I got a bachelor's in aerospace and aeronautical engineering. I love school so much, I'm joking, that I actually got a master's in project management and robotics much later at Johns Hopkins. And this is me as an intern a very long time ago, very long time ago. But what hasn't changed is I still use the engineering design process to develop space vehicles, the same thing you all are going to use today to develop your rocket. All right. So one thing in my job that I'm doing now is answering that question. What do we do with satellites when they die? What happens to satellites when they die, when they go bad? So I have a cool video to show you that's going to explain some of that.
What happens to old satellites? Typically, satellites, if they run out of fuel or something happens to it where it's just not working, it is essentially orbiting around the Earth dead. So what happens eventually is gravity will continuously pull on it and bring it down. If that satellite, upon re-entering into the atmosphere, does not burn up, sometimes you'll find pieces of that structure on one of our large continents or in the ocean. We don't want that to happen. So if a spacecraft ran out of fuel or has a bad part, it'd be great if we could fix it. That's why NASA is working on in-space servicing, assembly, and manufacturing capabilities. OSAM-1, On-Orbit Service and Assembly and Manufacturing Mission 1, is coming to you very soon. There are capabilities and technologies that will allow us to sustain some of our key assets. So if they have a bad instrument or they want to upgrade, we can do that in space. Essentially, that is going to help NASA explore and create missions that are going to improve our capabilities from the moon, Mars, and beyond. So what happens to old satellites? Well, currently, they either burn up upon reentry or they remain in space dead. But all that's going to change with OSAM-1. It's going to be the game changer that is going to help them become sustainable and upgradable for the future.
Awesome. So that's the mission that I'm working on right now. We actually sometimes call it Awesome One. That's the name of the mission. But I would love to hear from you all some. Let's get started. Let's get engaged. What comes to your mind when you think of space? Type it in the chat. Like, anything. What comes to your mind when you think about space? What comes to your mind when you think about space? What questions do you have? What things do you want to explore? Yeah. Bronx International, shout out to you all. Black holes, planets, gravity, gigantic, love it. The moon, the galaxies, outstanding. Space junk, yeah. The stars, yep, excellent. Mass, it's a lot of mass. The supernovas, you all are cooking now. It is a vacuum, that's excellent, great. Neil Armstrong, man, I really wanted to be an astronaut. New worlds, I'm hoping you all become astronauts. The galaxy's excellent. Thank you. Good. Tech prep. That's great. That's great, Natalie. All right. Coral reef. Excellent. Black holes. Hey, you all are killing it. Similar. Like, I wanted to know, are we alone in the universe, right? That's a huge question. Or is time travel possible? I mean, that's the only way we're really going to know if we are alone. Can we travel the speed of light? If we're going to go to distant planets, much beyond our Milky Way, we got to be able to travel much faster. All right, we have some trivia this afternoon for y'all to test some of that. And then someone said, and then also, what if we can't live on this earth any longer? I mean, I know we're trying with efforts like renewable energy and sustainable energy and monitoring the ozone layer to keep our planet intact. But what if we need to live somewhere else? I mean, these are all different things that come to my mind. And what's really cool is you all as space enthusiasts in your generation, I'm hoping you all have the opportunity to really investigate some of these crazy questions we have about space. But before we dive in, let's talk about the past. How did we get here? The past, all right? So first, we started off with Sputnik. Sputnik was like the first satellite to go to space. It was launched by the Soviet Union. And then there was the Mercury program. One thing about space you're learning is space is very, very competitive. So once Sputnik launched, definitely the United States wanted to get in the game and launch their own mission. And then once we started to launch, satellites into space and leaving people into space, we thought we really need to develop better rockets. And that's one reason why we're talking about rocket systems today. I like that St. Peter's, the Doppler effect. And then, we had the Space Shuttle Columbia, where with the space shuttle, multiple people were going into space almost every month, which was just crazy cool. And we really realized that we're wasting our rockets, right? Where it's expendable. So they thought, commercial folks got into the business like SpaceX and started to develop things like reusable rockets. I was absolutely blown away when I saw the SpaceX rocket launch and return. Unbelievable. But what's even more unbelievable is what you all will do. What are you going to develop in this next generation? So here's my next question for you. You can place it in the chat. Hey, Northeast, it says Space War. What do you want to investigate in space? Like, what are some things that you would, not just questions you want to answer, maybe specific places you want to go? You're the scientist, right? You're the head of NASA. You're the head of SpaceX. What do you want to investigate? New life. That's excellent. Yeah, that's a great one. Thank you, Bronx International. Excellent. Black holes. Live on Mars. I would love to live on Mars. I think that would be crazy. Colonize Mars. Water. Excellent, because if you have water out there, if you have new energy sources out there, if you have natural resources out there, then maybe that's a planet that can support life. Excellent. Grow plant. Yeah, we need plants. Excellent. The Alpha Centauri. Excellent. Nice, great. Here, this is how we categorize it at NASA. This is how we break it down. One, space communications. You got to be able to communicate. All of our systems are not autonomous. That means they don't all work by themselves. We need to get data back from the rover on Mars, right? And then there's navigating our planets. There's Earth and planetary science. How do we protect our world, right? How do we protect it even from the sun? The sun is that damaging radiation coming to our planet. And then we're building stuff in space because we want to colonize. You all talked about that. Space weather monitoring is huge. And then astrophysics. That's where I would love to live, in astrophysics. That's my science, because I want to go further and further and further out. Good. Life not from Earth, great. Kepler 452b, excellent. The infinity of space, liquid salt. You all are much smarter than me. All right, great. All right, so what do we send into space to achieve our mission? Well, we send all kinds of things. I thought we only sent astronauts at first, and an astronaut is a payload. But if we want to investigate, there's also satellites. Like in that top left corner, there's the James Webb Space Telescope, which is investigating in new wavelengths, crazy new wavelengths, everything about the origins of space. Ugh. And then you have rovers. You got to communicate with rovers on Mars. And then you even have the different systems that we're sending on the moon. So there are probes. That's excellent, Northeast High School. Yeah. And someone said the question, what is air pressure? Nice. All right, good. So a spacecraft is what you're going to investigate as well as part of this lab. And a spacecraft specifically has instruments that will execute the science that someone has thought of to investigate in space. So you're pretty familiar with like the Hubble Space Telescope and the ISS. All of these are different spacecraft. Now, this is a question that I hope we all know the answer to. How do we get our payloads into space? How do we get them into space? Like, what do we do to take all of our payloads into space? What are we using? First, you got to get there. Now, in addition to gravity, that's just something crazy that's to overcome, right? You saw that in the video that the rocket was just kind of sitting there, shaking and not moving. It's just trying to overcome that mass and that direct pull of gravity. But you also have to navigate through the atmosphere. I mean, in addition to the atmosphere having crazy temperature ranges, the friction, the resistance of friction, the movement of air, all of that is a challenge now to survive for that rocket, but also to overcome. So that's something you should think about as well when you're developing your rocket. Space is on our Earth, close to the Earth, we have a lot of air, but then when we're further out, it's a vacuum, and that transition is very difficult for sure to overcome. And you do that though by designing a very robust rocket. In rockets, we really need to invest in better rockets. And this is why we want to take larger and larger systems into space. We have a lot of stuff to take into space if we were to colonize the moon or Mars, right? I mean, you all talked about it earlier. We may have to take, things that materials to manufacture. We may have to take ways to hone in on our energy resources. That's a lot of mass. And for our rockets right now, 90% of the volume and the mass is the rocket. It's not the payload, the thing we actually want to take to space. Not a very efficient design. So part of you working on your rocket today, maybe you'll come up with some new ideas to develop new rockets, because we really, really need that, all right? But rockets get into space using their propulsion systems, and there's two propulsion systems. One is like 4th of July. If you've ever launched a bottle rocket, which my brother and I, we launched bottle rockets at each other. That's nuts. All the time. It's that instant energy, that instant propulsion. It's a solid rocket engine. You launch it and it's no coming back, right? You can't turn it off. You can't throttle it, nothing, right? And they're very powerful. That's the benefit though. It's extremely powerful. On the flip side, you have your liquid rocket engine. And with your liquid rocket engine, you can throttle it. You can slow it down. Maybe you can even not necessarily stop the engine, but stop the fuel that is oxidizing in that engine. But on the flip side, it's not as powerful. And you'll think about that when you develop your rocket. I mean, you may develop it in ways that you have multiple stages, which we'll talk about, that kind of gives you that throttling feel, okay? So now you have propulsion, and then now you have your challenge, okay? And this challenge is so much fun. So we've definitely experimented with this challenge over the summer and throughout the school year, and teams at schools have created rockets that were unbelievable. So what you're going to do, what we've given you, is the materials to develop a rocket in your own home. You're going to launch it from the base, from the floor, up to the ceiling, overcoming gravity, straight vertical. And on top of that, we're going to see if you can take a lot of mass up to the ceiling, right? A very efficient rocket. Because ultimately, we want to see if your rocket mass is much less than the payload that you're taking up to the ceiling, then you have like a really, really cool rocket. We want to see that. Maybe we'll even have a little rocket competition today. So you're going to construct a balloon-powered rocket that carries a payload to space, which is your ceiling, right? And you'll use the engineering design process. Very important process, because one, you start with researching. You start with thinking about creative ways to make a great, great rocket, and then you design it, hopefully on a sheet of paper. The more design, the more you include design in the process, I'll say that, you're going to have a much better build. And then after you build it, we want you to test it. We've given you enough materials, enough balloons, enough fishing line, enough straws, enough paper clips where you can test and test again. I've been blessed to really work on some innovative products, but I've never worked on a product that didn't fail multiple times. So we've given you that ability because you want to fail and fail fast. Because when you fail and fail fast, you're going to deploy the absolute best system. All right. So hopefully by you thinking about this problem, you're already coming up with some ideas, right? You know, are you coming up with some questions or some ideas about the project? How do you want to design it? Throw that in the chat. Anyone already have some ideas about their rocket? Anyone already watched this video and they're already building it? I love to hear from you all. Like, what are you thinking? Or are there some challenges that you're thinking about with developing this rocket? I'd love to hear about that as well. What are some ideas you have? What are some questions you have? Aerodynamics matter. Excellent. That's right. They do, even within your home, even in a controlled environment. Aerodynamics matter. Excellent, Northeast High School. That's great. Some other things to think about. Oh, yeah, how do you build around something that is expanding and contracting? Oh, Shelby at Shelby Rising City. Excellent question. Excellent question. How to keep the balloon attached when the volume changes. Nice. That's nice tech prep. Very good. It's a dynamic design. It's changing on you as it launches. You know, do you use tape? Do you use rubber bands? How are you going to secure this straw? Right? How do you overcome that friction just between the straw? The stability, man, maybe you use fins for stability. Maybe the spin, like, energy, your energy could go towards the rocket spinning a lot and being unstable, or the energy could go towards focusing on the rocket going straight from bottom to top. You have to control that with stability. Excellent questions. Maybe fins. So other questions you may have is my rocket strong enough? What if it stops midstream? Well, maybe you create multi-stages of rockets. One rocket starts your propelling action, and then when it depletes, there's another rocket that takes you all the way to the top. That's staging. Or maybe you say, no, I don't want to stage it. I'm going to throw 3 or 4 rockets all together at one time, and I'm just going to give it the absolute most energy and force I could propel it with and take it all the way to the top, right? That is another option, right? There's so many different ideas. I love this Riverton Street Charter. Will it pop once it launches? That is the biggest challenge in space. Once we launch, if something fails, we can't just fix it, right? I mean, I know that project I talked about, OSAM-1, hopefully we start fixing satellites in space, but most time, once your rocket launches, we can't fix it. So you got to practice this a little bit. How do you make it a little more reliable? That's an excellent question. Is the material strong enough? Excellent, Duval, to overcome that gravitational pull. Man, nice. All right, good. So then we talk some about staging. That's, there's multiple rockets that are burned at different times to take advantage of dead weight, right? So sometimes rockets will have 3 stages. They'll have a stage to just get us off the ground. They'll have a stage to drive us towards that final orbit. and then they'll have another stage that will place the satellite in its orbit. And that's because, you know, you want to get rid of that heavy weight and stop carrying dead weight if you no longer have any fuel. This is good. Excellent. All right. I'm getting excited. I'm getting excited. So here's some examples for you. All right. This is Katie, and this is just her working through the process of actually, you know, building. Like she chose the biggest balloon possible that she could use. And you can see like a really different, innovative way that she's going to carry her paper clips. You can come up with any ideas you have as well. She's loading on her straws because those straws are now going to have to guide this rocket up this the fishing reel that we've given you. And then you can see her trying. And I'm not going to show you a successful video, right? I'm going to show you the challenge. I'm going to show you the journey, right? And then in the wrap up, I'll show you her very successful rocket. But look at that. Did you see it? Some of you all, I'm going to show that again. Some of y'all hit the nail on the head. What if it pops? Great questions. Is the energy being used efficiently in this rocket? It's kind of twirling and twisting. It's moving around. The rocket is kind of gliding. It's pushing itself against the fishing line. Is that an efficient way to use the energy? Hopefully, through this partial success, but partial failure that you see in this rocket video, it inspires you to come up with some ideas to solve the problem and make your rocket the best. And again, what we want to see when we bring you back for the wrap up is a rocket that launches fast and launches the most possible weight it can, because then, you know, maybe we can colonize Mars, right? Maybe we can travel all the way to Pluto and different asteroids. I mean, that's the game, right? So Emma Messer says the balloon creates thrust when you release air from it. However, it's not really flying in a straight line. You need something on both sides to stabilize it. That's excellent. Excellent. All right. So we really hope that you are just getting absolutely excited about this lab. We do want to highlight this though. I mean, even now, even before the wrap up, ways that you can get involved. Like I'm involved through a government agencies. Like NASA has, the United States has NASA, Europe has ESA, Japan has JAXA. That's great. But what's really, really pushed the space industry is commercialization. You know, the competition across the country and the world of commercial entities seeing that space isn't just cool, but there could be opportunities to build jobs, to make a profit. That's been great for us. That's been great. Like NASA, we don't build rockets anymore. We focus on science. We let industry build the rockets. And they do a great job at it. But then there's also universities that are performing a lot of different research, partnering with scientists, building a bigger team to investigate and explore different things about our world. And that's where we see you all getting involved. Like you're getting involved right now, which is crazy great. And you also hope you get involved with internships, which we'll talk about in the wrap up. But one, if you're in the space, you should target one of these great schools. I'm pretty biased towards Purdue. I think Betsy is as well. We're these crazy schools for sure to get involved with. All right. Okay, that's right, Boiler Up. You got it, Betsy. So in addition, there's another activity that we would like you to perform. Like if you find some time while you're developing the rocket, while you're building it, or if you're working in teams, maybe one of you all could try this spacecraft docking simulation. I mean, I think it's funner than a video game. What you're gonna do is now just imagine you've completed your rocket. Now what we're doing is we're simulating your rocket, taking the payload that you launched to the ceiling into space, but how are you gonna transport food or astronauts to the International Space Station? Well, we have this like docking simulation where you're gonna, balance out the forces in space. You're gonna use your changes in translation, your changes in speed, your changes in rotational movement to navigate this capsule to the International Space Station. That's another project for you. And I think it's gonna be a lot of fun as well. All right. So with that, I'll just say, hey, thank you all so much for the opportunity to present this intro to you, and I'm going to hand it off to the outstanding and wonderful. Is it going to be Monica and Constance? Are we double dipping? What? To
Uh,
teach you all
we have the whole ET team here, but I'm going to take the lead on this one, and I'm going to just put up our agenda so that you guys can all see. Right now, we're going to open up the breakout rooms, and we have some amazing mentors here who are going to be leading those sessions for you. If you have any questions, you can hop right into those breakout rooms. We are also going to, oh, they opened up right away. So please feel free to hop in there. And let me just